Okay, thank you. Well, thank you for inviting me, and I really enjoyed Tay's talks. They were fantastic. So thanks to all the speakers that came before me. I'm going to talk about, I put the word surprises up here because, you know, climate science has become the dismal science, right? We depress everybody when we give these talks. But surprises could be positive or negative, right? And I'll point out which that is as we go along here. But as a teaser, unfortunately, this could be how to be more depressing than Al Gore in less than 45 minutes. But I'm going to try not to do that, if possible. So here's an outline of what I'm going to talk about. I'm going to talk about sort of two stories. One is what I would consider to be not yet fully reported story. That doesn't mean it hasn't been discussed within the broad media, but I don't think it's really been fully elaborated, and I think it has a lot of important issues. And it is this feedback between the climate system and the global carbon cycle. That led me sort of on a journey, and I'm going to explain some of that work, which was understanding our fossil fuel footprint in a lot more detail than we have in the past. The second thing is going to be right at the end, and it's going to be short, and it's kind of what I'll call a teaser. But it's also what I would consider to be actually a not at all reported story, which is emerging, and I think is going to be very, very important, and is going to create some real problems in the climate negotiations, which are, of course, coming up in 2 months or 2.5 months. So first, quickly, the carbon cycle, the global carbon cycle. Most of you know carbon dioxide. That's the most notable feature of the global carbon cycle. But you can break it down into very simple sort of three reservoirs: the atmosphere, the oceans, and the biosphere. And in the atmosphere, of course, carbon is mostly as carbon dioxide, CO2. In the oceans, it's mostly carbonate and bicarbonate, also calcium carbonate. And on land, it's, of course, tied up in all sorts of organic molecules. And then, of course, the largest amount in the whole system is in rock, of which there's an enormous amount, but most of that is essentially inaccessible. Hence, we don't tend to think of it as part of the sort of active system of the carbon cycle. Now, this is pre-industrial. This is before we began to interfere or perturb this system. And pre-industrially, there were these fluxes every single year between the atmosphere and the oceans and the atmosphere and the land. And those units, by the way, are billion tons of carbon, billion tons of carbon. So if a car is about a ton, every year, the atmosphere and the ocean exchange 100 billion tons of carbon. It's absolutely astounding. 90. The land exchange is about 120. Now, you know the land one. That's the one you see all the time. In the spring, all the trees around the planet put on leaves, and they essentially suck down not all, but they suck down a large proportion of CO2 in the atmosphere. And then in the fall or in senescence, all the leaves fall off the trees, they go into the soil, microbes chomp on those, and that CO2 goes right back up. And it's just an annual cycle. It's been going on for a long time. In the oceans, there's also a cycle. It's a little more complicated, but it's essentially the same order of magnitude. But in the annual mean, that is across an entire year pre-industrially, there's a net exchange between these reservoirs. The atmosphere was essentially neutral to the biosphere and the oceans. Of course, we've changed that picture. Now, if you go back very far in time, things were not that steady. First, I'll show, this is in the last 1,000 years, the year 1000, it's the year 2000. And as you can see, prior to sort of industrialization, this is the amount of CO2 in the atmosphere. It's pretty steady. Well, there's a few little dips and wiggles there, but generally pretty steady. If you go back further, there are actually lots of big giant dips and wiggles. But those are well understood and associated with essentially orbital mechanics of the planet. The planet does not orbit the sun in a regular way. It's got a little bit of wobble. The Earth actually wobbles on its axis a tiny bit, and that has caused variations in temperature and CO2. But they're fairly well understood. Of course, here we are. You know, this is the Al Gore moment, right? Here we are at this sort of, you know, red bar flying up through the top of the screen. So we're leaving or exiting what, at least for the last 650,000 years, has been a relatively steady, or at least understood variation in atmospheric CO2. Right. And of course, if we keep going as we're going now, we're now at about 390 parts per million of CO2 in the atmosphere. If we continue as we're going now, we're going to get up to something like 700 to 900 parts per million by the end of the century. A lot of CO2. So we came into this system, and we come in two very fundamental ways. One is through the combustion of fossil fuels, which you all probably know about, which right now is emitting about 7 billion tons of carbon every year into the Earth's atmosphere. We also have engaged in massive manipulation of vegetation at the surface, primarily tropical deforestation. That emits roughly 1.5 to 2 billion tons every single year for a total right now of about 9. Okay, so 9 is coming from the anthroposphere. It's going into the atmosphere. Of course, these gigantic fluxes that pre-industrially were neutral, and we've perturbed that system. Now, by the way, it's always worth noting that though we emit about 7 billion tons every year, there are still about 5 to 10,000 billion tons of carbon in fossil reserves still available, mostly in coal, of course. So still a lot out there that we could oxidize if we choose to. Now, what has that done? We can go into the atmosphere and we can measure a rise every year of about 3 billion tons, right? Now, we're putting 9 into the atmosphere. The atmosphere sees about 3. Actually, this number is a little bit low. It's a little more than that. That clearly doesn't balance. And what's happening is we've been driving these other parts of the system out of balance. We're forcing CO2 into the biosphere, and we're forcing CO2 into the oceans. Now, this is very lucky. If that wasn't happening, the emissions into the atmosphere every year would be a lot bigger. They'd be a number more like 9. Instead of what they are is about 3 or 4. So we're kind of lucky. We're getting a helping hand from the biosphere and the oceans. Very, very lucky. Of course, there's an unfortunate outcome of all that. Now, this is relatively well understood. It's a simple concept where if you took a beaker of water and you put a lid on it and you left an airspace and you injected some CO2 into that airspace, a certain amount would dissolve in the water. CO2 is soluble in water. We're effectively pumping the Earth's atmosphere up with CO2 and hence driving more CO2 into the oceans simply because CO2 is soluble in ocean water. The biosphere is a lot more complicated, and in fact is so complicated it's come to be called the missing sink. Missing because for the longest time, and in many ways still, we don't really understand what's going on, where all this carbon is going. And so many of us have spent a long time hunting for the missing sink. And there are sort of 4 hypotheses to explain what's going on in the biosphere. And all of them, except for one, actually directly or indirectly involve us. The first one is referred to broadly as carbon fertilization, which just says that as plants have more available ambient CO2 around them, which of course is their food, they become more water use efficient, or they take up more CO2, but they basically have more food to eat, in simple terms, and so they can get a bit bigger. The other one is similar, that every time you burn a fossil fuel, in fact, anytime you burn anything at high temperature, you actually burn some of the air, right? Air is mostly nitrogen. And so you oxidize a bit of nitrogen, that goes up into the atmosphere, that rains out downwind of large industrial or urbanized areas, and the mid-latitudes, at least, are nitrogen-starved. Hence, we're fertilizing large areas of the mid-latitudes as we essentially burn some of the air. The third is climate variability itself, that maybe the planet, as it gets slightly warmer, maybe precipitation's changing, it's more favorable for the biosphere in general terms, and hence the biosphere is getting a bit bigger. And finally, the one that's probably most obvious to everybody is just basic forestry growth or management of the biosphere itself. The best example of that is, if anybody's from New England, I lived there for a while, and I would go out walking in the forest, and of course you'd come across all these old stone walls. And those are the outlines of all the old agricultural fields. That was the first place we engaged in agricultural activity in the United States, and which we abandoned when we found, the lovely grasslands in the Midwest. And those forests are now regrowing. In fact, that area used to be about 80% non-forest. So it was about 20% forest cover, 80% open agricultural land in New England. It's now exactly the opposite. So there's a lot of regrowth, and those trees have not reached maturity. Now, there's many other examples around the planet where this has happened, and it could be that that's happened at a large enough scale to account for that 3 billion tons that goes missing every year into the biosphere. And most likely, it's a combination of all 4, and it depends on where you are. But many of us are looking all around the planet to try to understand which of these is acting when and where. Now you might ask, why should we care about this? What's the big deal? And of course there's two, I think, broad reasons. One is there's lots of neat science involved in understanding what's going on with the missing sink. You can learn a lot about the biosphere, how microbes work, turnover times in the biosphere, et cetera. Lots of great things. But the real policy-driven reason is that, in fact, if that missing sink, that helpful 3 billion tons that's occurring in the biosphere every year, and the 2 billion tons or 3 billion tons in the ocean were to saturate, it would make emissions look twice as bad as they are now. Now that's really a bummer, right? I mean, that's essentially increases the severity of the emissions problem by a factor of 2. So here is a simulation. This is a bit busy, and I'll explain it to you. These are two models. These are two climate models. Okay, one's the red model, one's the blue model. Here's, for most of you, will recognize this type of plot, right? Here we are at 1850 on the left-hand side, going up to the year 2100 here. This is global mean temperature. Those are two models. They've been driven by exactly the same fossil fuel emissions portfolio over the future. Exactly the same. The only thing that's different between these two models is how the biosphere interacts with the atmosphere. In other words, is there carbon fertilization? Is there nitrogen fertilization? Is there land use change? What's going on? Also how they couple with the oceans. Now up here is the net flux between the oceans and the atmosphere. Let's go to the year 2000. Here we are at about 2 billion tons removal every year, as I showed you in that sort of big reservoir bubble plot, right? Both models show that as we continue to emit fossil fuel CO2 into the atmosphere, the oceans actually keep uptaking a little bit more. They sort of try to keep up. The red model looks like it starts to saturate and flatten out. It hits a limit. It doesn't seem it can do any more. It's sort of done its job, and it sticks at around something like 4 or 5 billion tons, whereas the blue model continues to take up CO2. And when you go to the land, it's a very different story. Here we are at the year 2000. Here's our sort of 3-4 billion tons. They're both about here. The blue model looks like, you know, it continues to take up a bit more, and then it starts to saturate somewhere out in the latter half of the 21st century. The red model, on the other hand, does something very, very surprising and obviously very worrisome. Not only does the biosphere no longer take up the 3 to 4 billion tons, it turns into a source. It starts emitting CO2 into the atmosphere. Now this result is actually 3-4 years old, but believe it or not, in the last IPCC round, of which I'm involved, we weren't actually able to get these coupled models into the results. So it didn't come out in the IPCC reports. It will come out in the next round. Sure. Yeah, and most of it is the underlying physics and biology that is sort of built into the models. They're both doing roughly the same thing. They're climate models, and they have biospheres and they have oceans, but maybe the mathematics is slightly different, the parameterization is slightly different. Climate models do have differences from one to the next, but it turns out that when you couple them to the biosphere, couple them to the land surface, they really exhibit different behavior. It's a very complicated thing to do. There's a lot of unknowns, et cetera. But what's really going on in the red model is two things. The entire tropical forests go into complete drought stress and die. So all the carbon in the tropics goes flushing out into the atmosphere. Now, actually, initially when this paper was released, a lot of the stories used that as the primary explanation. It turns out it's not. It was only 1/3 of the effect. 2/3 of the effect was carbon all around the planet coming out of just soil. Very boring, not very exciting, just soil. That basically microbial activity increased, the planet's a little bit warmer, soils that are in permafrost a lot of the year, are in permafrost less of the year, and you start oxidizing all this old carbon. You start mining it, essentially. 2/3 is coming out of the soils everywhere, mainly in the boreal regions where there's a lot of deep, deep, dark, old, frozen carbon. We start mining it. So Something to be worried about. Now, the question is, which of those two worlds is correct? Is it the red world or the blue world? Of course, there's a lot of other studies now, and there's sort of a big range of models. I've only showed you two, but it's still not clear which of these two worlds is the real one, or the one that we will run into if we keep going the way we are. One way to figure that out is to look at atmospheric CO2 itself and look at its very fine variations around the planet and allow that to give us a glimpse into how the planet is functioning now. And I'll explain that in a minute. This is sort of the beginning trace of how you might look at CO2 in the atmosphere. This is a curve you've probably all seen. It's a very famous curve by Keeling. This is measured, CO2 measured on the top of Mauna Loa in Hawaii, 12,500 feet, in the middle of the Pacific Ocean. I find this curve the most amazing thing. And 1957 up to the present, and you see the nice, monotonic rise, which is, of course, just driven by fossil fuel CO2 going into the atmosphere a year. And you see these wonderful wiggles. And the wiggles are the biosphere breathing. It's actually that 120 billion tons going back and forth every year, right? Trees leaf out, they senesce, the CO2 just goes back and forth, superimposed on the monotonic rise driven by fossil fuel CO2. Very sort of simple story. Now, you can actually look at this in more of a sort of magic carpet way. And here we have now CO2 on this axis in our parts per million unit going up. Now this is the North Pole, the South Pole, and then going off in time in that direction. There's a few things that are really interesting about this. First, you see that wiggle in the northern hemisphere up and down with the seasons. You sort of see the monotonic rise. And you also see a complete and total phase as you go into the southern hemisphere, where the seasons are opposite what they are in the northern hemisphere. And of course, since the southern hemisphere is mostly ocean, you don't see the big giant wiggles that you see in the north, which is predominantly land. So a lot of information embedded in a plot like this. Turns out you can even look a little bit closer. This is now a simulation. This is not observations. This is a simulation in a transport model in which we drive biospheric activity into the atmosphere. And you see, here we are going into winter. You see this rise of CO2 in the northern hemisphere as we go into senescence. And as we go into the growing season, it's going to suck it all down. The reason I show this is that CO2, when you look at it closely, looks like weather. And it should look like weather. It's certainly reflective of the sources at the surface, but it's also just a passive gas that gets blown around, just like everything else. And it looks like weather. Turns out we can use these patterns, these space-time patterns, to infer where sources and sinks of carbon are. In other words, we can use the space-time patterns to maybe figure out where that 3 billion tons is. It's called an inversion, atmospheric inversion. Everyone does inversions in their daily life, right? Let's say you're standing in your backyard and you might smell a barbecue, right? And you sort of think, okay, which way is the wind blowing? How strong is it? Oh, it's probably in that direction. You're doing an inversion. You're actually taking the endpoint of a series of events and with a fairly limited amount of information, inferring what sort of happens upstream. So we take a very complicated mathematical approach to do just that with CO2 in the atmosphere and try to figure out, given these patterns, where the CO2 is coming from and going to try to find that missing sink. Now, what I'm going to show you is some results. This is also a movie in which we look at the last 25 years and we ask the question, if you were to take these inferred fluxes that I just described, right? That 3 billion tons that's distributed all around the planet, and you were to correlate it with temperature, what would those correlations look like? And the reason this is important is because going back to the blue and red model, the thing that's key here is the relationship between temperature and carbon. In other words, in the future, if it gets warmer, does carbon come out of this system? Does it saturate? Does it go nowhere? What does it do? So we decided to look through the last 25 years and see if there's a relationship between these two things. And what you're going to see is basically as these two time series coincide in time, the planet's going to light up. The tropics are going to light up. So I'll run it forward. I think these are in, I can't remember what the time increment is like. It's a month. But as the time series come together, whoosh, the entire tropics light up. And what that looks like, and what it really is the El Nino Southern Oscillation. Probably most of you have heard of this. It's a point comes every 3 to 7 years, in which the tropical Pacific warms up. Causes all sorts of funny weather in various places. I don't know what it does here in Austin, but it has a weather effect all around the planet. And sure enough, we see it in the relationship between temperature and carbon. Well, that's kind of nice because it gives a bit of an indication that, okay, so when temperatures go up from the sort of wiggles due to El Nino Southern Oscillation, carbon comes out of the system. That might give us an indication that maybe it is, in fact, the red model that's the right one of those two. Now, I say suggestive, and it's not, doesn't confirm the choice of the red versus the blue model, because there's, unfortunately, like everything in science, lots and lots of uncertainty and things that, you know, could easily go wrong and we're not too certain, et cetera. And there's two sort of things that create problems for choosing the red model over blue model, given what I just showed you. And one is the fact that the only way we can really figure that out is we have to assume that we know what this is very, very well. We also have to actually assume that we know what this is, because when we look in the atmosphere at CO2, we can actually separate these different fluxes because they all are CO2. There's no magic tag on a CO2 molecule that says I came from fossil fuel versus I came from a plant, or versus I came from the Pacific Ocean. It is, but it's not very good. There are isotopic signatures, but they're really tough to separate. So what we have to do is we have to assume we know those two, and then we basically solve for the one that we don't know. Well, it turns out that we thought we knew this really, really well, but we don't. We don't know it. And the other problem is that when we measure CO2 in the atmosphere, we don't really actually have a lot of places where we measure it. I showed you the measurements at the top of Mauna Loa in Hawaii, and that's a very famous measurement. There are only about 100 of those around the planet. Single points, dots, around a very large planet that's very complicated. We measure CO2 at about 100 places, and that just is not enough. It's not enough fidelity. It's not enough eyeballs on the system. So a satellite was supposed to be launched this last year, and unfortunately, it didn't make it into orbit. And it was going to measure CO2 everywhere around the planet from a remote sensing platform. And I was on vacation at the time when the launch occurred. We'd all been sort of anticipating this for a long time, and I was on vacation in the jungle of Nicaragua, and I did the stupid thing that I know I should never do, which is check my email while on vacation. Never, never, never do that, because you know it's going to be bad news. It just can't be good news, right? So I got this email, and then, I don't know, got a six-pack of beer and went to the beach. So it was very sad, but there actually is a Japanese instrument that went up a month before that's close enough that we can use it. It's going to be okay. But two big things. So we don't have enough CO2 measurements, and it turns out we didn't know fossil fuel as well as we thought we did. Now, this is a map of fossil fuel CO2 emissions. Now, it looks probably like most of you would guess, and maybe you've seen this picture. Three big giant bullseyes around the planet, of course, the United States, Europe, and East Asia, Southeast Asia. But if you were to zoom in on the United States, this is what that information would look like. This is about vintage, 3-4 years ago. It's pretty hard. And really what this is it's not even as good as it looks. Really what it is it's the national amount of fossil fuel CO2 that's emitted that's just distributed by population density. Now, population's probably a pretty good proxy for where we're emitting CO2, but not really, right? I mean, interstate highways, power plants are not near people anymore because we don't like them. And so we sort of took a look at this and we said, oh gosh, this is terrible. We really don't know any better than this where all the CO2 is coming from, which is kind of hard to believe given how important that flux is. So we set ourselves off to try to do a better job. And we called this project Vulcan, for the Roman god of fire. And we busily went off and tried to figure out basically where all the fossil fuel combustion is occurring. And I'll just show you a quick few pictures of what this looks like. This is the transportation sector, so we've imaged and quantified all the roadways in the United States, all the airports, all their flight paths, snowmobiles, anything that moves. we've tried to quantify. We have all the industrial sources. Again, this was relatively well known, not for CO2, but we know where they are. And so we had lots of tricks and bells and whistles to try to quantify all this. And here is the combined sort of residential and commercial sectors. This is the building sector. This is, mainly due to space heating and conditioning across the United States. And this is where all the power plants are. That, of course, is also relatively well known. And we put it all together, and we get this really nice, much more detailed map. Now, it's a map, it's a picture, but of course, there's lots of quantitative information in this, and a lot of detail that we are now using to try to go back and solve that first problem I mentioned, which is, where's the missing sink? Where's the biological part of the CO2 exchange? Now, we took this and we transported it through the atmosphere and made this. I had never done this before, made a YouTube video and put it up on YouTube. And I thought, my mother and somebody else would probably look at it. But sure enough, there was a lot of interest in this. And much to my surprise, over a couple 100,000 views, over 100,000 in the first few days. And really amazing. I mean, it's not, a Paris Hilton video, but it's not bad for science, right? And I really think that a lot of what was so interesting is that this heretofore invisible gas that we've all heard about and know about, we've never really been able to see. And this gives you a glimpse into really what it looks like. This is what it looks like. This is the breathing of the United States every day as we wake up and as we go to sleep and as we cycle through our activities. It builds up over time. We have these amazing sort of, this is in the summer, so you get these actual tunneling thunderstorms that bring blobs of high CO2 air up into the atmosphere. Anyway, lots of wonderful science can be done with the transport realization of these fluxes. And so we've set off doing all sorts of things that we didn't originally intend to do, but now because of the sort of a lot of new information due to this, we're able to sort of answer some cool and interesting questions. Now we've put all this on Google Earth, of course. Anybody who has anything that's geographic, you're immediately told it must be on Google Earth, whether you like it or not. Somebody from Google will show up at your door and make you do it, right? So we've done that, and yeah, you can go in and explore emissions in all states, counties, down to sources, power plants, airports, everything. Okay, so we're moving on, and we're trying to even make this better. And I put this up because this is a funny story, or at least I thought it was funny, that we initially, when we did this, had relatively limited information about traffic in the United States. We had some data, but it really wasn't that good. And I was very frustrated by this because I know that there's lots of traffic data that's collected. It's collected all the time in every city and across states, counties, but it wasn't organized anywhere. And so an enterprising graduate student of mine filed a FOIA request, something that it hadn't occurred to me to do. And the best part is he was from India. So he filed a FOIA request with the federal government to get all their traffic monitoring data. And sure enough, 6 months later, thousands and thousands of data points showed up with wonderful data that's all very detailed. So for example, you can go to a point. This is in a location in rural Utah. And this is a weekday. This is the traffic flow at an intersection on a rural Utah weekday. And here it is on Sunday. And what do you think? What do you think the Blitz are? Exactly. It's funny. I give a talk to a room of scientists, and they all bunch of atheists, right? But it's church. So it's wonderful. We have all this. So the point here is that we have massive amounts of data, I would argue, lots of information, but we don't point it at this problem. And we haven't pointed it at this problem, which is amazing to me, given how large and monumental this problem is. Sitting on all this information, and we just need to sort of turn our sights on it in a certain way. And so we've begun to move along and add more detail. And in the process of doing that, we had a lot of requests from people more down at the sort of almost street level. Now, what I showed you a minute ago looks very impressive and it looks very detailed, but it's still coarse. I mean, yes, we do the roads, but in the building sector, we're really quantifying things about 10 kilometers on a side. Okay, that's still kind of big. So we thought, well, maybe we could zoom in and actually try to quantify things in a real cityscape. And everybody in a certain, not everybody, but many people are doing carbon footprinting everywhere, right? At Purdue University, we had a class, and the students footprinted the university, and it's sort of like a cottage industry. But I would argue that everybody individually doing this footprinting is an incredible waste of time, because really we should just do it once, and we should do it with a lot of detail, and do it with a lot of science, and not have everybody running around doing all these different types of footprinting. So we decided to take a crack at a city. This is Indianapolis, which is an hour from Purdue. This project we call Hestia, which is the Greek goddess of the hearth fire. I don't like acronyms, so I stay away from them, and now I've sort of named everything using mythology. So we've now footprinted every single structure in the city of Indianapolis, all 50,000 buildings. We've footprinted, and we do that by running a building thermodynamic energy model on every single structure. And again, the data's there to do it, and plenty of computers are around to do it, and we're able to quantify all the buildings, we're able to do all the traffic, all the streets, everything. Down to a fair amount of detail, including, the time structure of the day of the week, the time structure of the hour of the day, when do people wake up, et cetera, et cetera. Okay, lots of accounting. Now, we're thinking about next steps in this effort in which one might be able to actually build some scenario ability. I mean, one of the many questions we get is, that's great, you can tell us all our emissions, but what we really need to know is if we tried this policy or that policy, we put in insulation in this part of town, or we changed our cars from gasoline to ethanol, what would happen? And so we're starting to think about building in some sort of scenario capability so that you could zoom in anywhere and ask the system a series of questions, and it would be able to give you changes in carbon emissions, maybe changes in how much it would cost, et cetera, amount of energy saved. We've also been thinking about this idea of leveraging Web 2.0 as a concept. And by that I mean that the real barrier, the real limit to really getting down in scale is getting everybody's power, energy, billing information. Now, I would love to have everybody give me their bills. That would be great. Now, you probably don't want to do that. At least you probably wouldn't want to give it to me. You might want to give it to somebody else. But that would really be an incredible thing. We'd be able to have very high fidelity information about what everyone's doing. Now, I don't suspect everyone wants to do that, but there are plenty of people who would want to do it. And in a good statistical, stratified way, we just need a good sample. If we have a good sample, we can start to build real statistics and really dial down on this problem, and presumably save people a lot of money and contribute to, for example, a carbon trading system, which there's a lot of interest in. I gave a talk recently for the first time to the CIA. I had never done that before, which was kind of weird, because it turns out that they're really, when I gave this talk, everyone's sort of sitting like this, and they all have white shirts and ties on, and there were actually people at the back of the room that were wearing sunglasses, which I just thought was, But they're interested because for any form of treaty verification, we have to have some sort of system to actually verify what people are doing. Other countries, the United States, and we don't have it. We don't have this type of thing. We also could do carbon forecasting. So we could do, just like weather, you could turn on your TV and maybe there'd be a short-term carbon emissions forecast. And we'd catch up to real time, and the model would assimilate the actual data, and just like a weather forecasting system, it would learn. This is what weather forecast models do. They really actually learn time. So a lot of neat ideas, a lot of places to go. Okay, now I'm going to come back to the thing I said in the outset in my outline about this teaser. So I'm going to shift gears away again. I started with the biosphere, I moved into fossil fuels, and now I'm going to go back to the biosphere again. What this is a climate model simulation in which the modelers stripped away all the trees in 3 different big latitude bands around the planet. Now, the thing we always worry about, of course, with fossil fuel and biosphere interaction is the carbon. There's other greenhouse gases, of course, but we know that CO2 is the big hammer in the system. It's the dominant greenhouse gas. It has all these problems in understanding where it's coming and where it's going, but it turns out There's other things that go on around the planet when we manipulate the surface. Now, we've known this for a long time, but we've never really had the computational tools that would allow us to explore it, and really only until recently. So what this is this climate model. They went in and they stripped away all the trees. They stripped away all the trees up in the boreal latitudes. They stripped away all the trees in the mid-latitudes. They went to the tropics and they did the same. And it turns out that when you do this, the bigger effect in the boreal regions, for example, is not the CO2. Now, there are a lot of trees in the boreal latitudes. The Siberian forests are enormous. But it turns out that it's the reflectivity that really matters. And it turns out that that reflectivity overwhelms the warming from the CO2. In the upper panel there, that blue color, that's all colder. It gets colder. Even though you've pumped all the CO2 into the atmosphere from stripping down all these trees, it gets colder because the surface is brighter. Yes, well, it's in the blue, sort of in the blue areas. Yes. And that's because trees are dark. They're, pretty basic, right? I mean, they're very, very dark, and they absorb a lot of radiation. And when you take them away, you expose a lot of snow-covered surface. Again, it's not that this wasn't known, but we've never really had proper coupled land surface atmosphere models with the sort of fidelity and the computational power to really explore this in anything that is remotely reliable. People have run sort of intermediate complexity models in the past, but they're so coarse you can't really trust what you get. I'm not suggesting you should trust this, but we've moved a lot closer. And this is quite surprising. Now in the tropics, the problem is not only is this a bit counterintuitive, but it depends on where you are, which makes the story much worse. Because when you're in the tropics and you do this, it has the opposite effect. Because in the tropics, when you remove the trees, you essentially remove the source of water to the atmosphere. Most of the water in the atmosphere in the tropics is recycled. It's coming out of the trees. It's just cycling between the atmosphere and the trees. They're the source of clouds. So you remove the trees, you lower the amount of clouds, you lower the reflectivity, and you actually get warmer. So tropical deforestation actually has a positive feedback with warming. Not only is it not just in the tropics, it's all around the planet. And in fact, it's most vigorous at high latitudes. In the mid-latitudes, when you strip away the trees, it's kind of murky. You sort of get both effects. Some places get cooler, some places get warmer. The reason why I consider this to be a very difficult problem, there's lots of difficulty in terms of science, but think for a minute about the policy environment. I had the good luck to be in Kyoto in '97 and The Hague in 2000 negotiations, and it's a very difficult environment in which decision-making gets made. It's very, very complicated. Everyone's horse trading. But this problem, for example, let's take the United States. This is a case where if you strip away all the trees in the US, you cool the US, but you actually warm some other places. Think about a country strategizing about their policy. They now have the counterintuitive incentive to potentially deforest as a way of actually counteracting climate change. I'm not suggesting countries are going to do this, but it creates makes a problem that was hard, much harder. Yeah?
What's the time scale?
Yeah, sorry, this was at the end of the century. This is sort of at the end of, running out 100 years. So right, it's not a near-term thing. Again, this sort of typical run 100 years and look at the, to equilibrium and look at the system. And in fact, I'm involved in a group right now in which we're trying to simulate with even finer resolution models domains just like the United States. Now, no one's going to strip away all their trees, but there's strong incentives both within international policy and now coming down within domestic policy to engage in afforestation, reforestation, et cetera, as a way to counteract climate change. But unfortunately, when you take in biophysics or radiative effects, by adding trees, you actually could be darkening your surface. And thereby, and it depends on where that is. Yeah?
What was the net effect when they ran the whole, stripping away the trees from top to bottom?
Well, it's much the combination of kind of what you see, right? You see warming in the tropics, cooling in the high latitudes, and this sort of murky picture in the middle. I mean, sort of overlap these three, and that's essentially what you get.
I guess I'm asking, is the cooling in the north ultimately greater than the other effects, or is the warming in the tropics ultimately greater than the other effects?
Oh, I see, right. Well, good question. I think that in the end, the net was cooling in the boreal latitudes modified by obviously this, but that was a much greater effect. So you get a net cooling in the high latitudes, a net warming in the tropics, and sort of a murky mixed picture in the middle. Yeah.
This might be a dumb question, but you're assuming it's still cold enough to snow, right? And have more white ground reflect off.
Yeah. Yeah.
I mean, did you assume that though?
No, it is, because, even with equilibrium climate change, you don't, while we lose sea ice in the Arctic, we don't sort of, the planet doesn't become, even in 100 years, completely snow-free. There's still winter, and there's still snow. But you're sort of revealing the snow more and more as you strip the trees away. Yeah? Correct. It is. Yeah. That's what's in many ways so surprising. Now, again, this is one model, and this work is relatively new, and there are people who are now trying to reproduce this, including us. We're trying to, instead of stripping trees away in this sort of broad brush way that's been done, because that's not the way the world works, we're trying to engage in sort of realistic deforestation and herringbone patterns in different parts of the tropics and see are there tipping points. In other words, is this phenomenon something that has a threshold associated with it, or is it a smooth transition? And most likely, it looks right now that it's a tipping point phenomenon. Just like you've probably heard about tipping points in other parts of the Earth system associated with climate change, this looks like another one. That's why I say it's sort of a depressing story, but it's an important one. Now, if you zero in on the tropics, you can even think of things getting yet more complicated. And this is just a picture, actually, of deforestation now and then potentially deforestation in the future. And the problem is that deforestation in many of these places is part of, or at least in the tropics primarily, is part of this kind of three-part cycle of deforestation, fire, and drought. As you deforest, you tend to remove your moisture source. That leads to drought, which leads to fire, which leads to more deforestation, et cetera. You get yourself caught in this kind of vicious cycle of tree removal. The problem is, as you add climate change to that unfortunate dynamic, it looks like it makes that problem worse. And that's one of the things that we're trying to explore right now by running more realistic deforestation scenarios in which we actually put human agents into the model. So people are on the ground making decisions. It's a simple sort of decision set. Should I grow soy, or should I leave the trees alone, or what should I do, based on a simple rule set of the price of agricultural commodities, how much rainfall, et cetera, to try to see if, when you do this in a little more realistic fashion, does this problem still emerge? So to conclude, I would say that, I'll say three things. Emerging research on the terrestrial carbon climate feedback, that first sort of missing sink problem that I identified, it indicates that a carbon tipping point looks like it's more likely. In other words, the system looks like, as the planet gets warmer, indeed it's the red model. Looks more likely than the blue model. It looks more likely that as the planet gets warmer, carbon comes out of the system. It doesn't just saturate, but it looks more likely that it really could turn around and we could start mining carbon out of the system based on past coupled variations between carbon and temperatures. Quantification of fossil fuel CO2, this thing we had to go back and do in order to sort of solve this problem better, can now be achieved at fine space-time scales, and it led to all sorts of other things that were really interesting and I think have a lot of benefits, not just science, but clearly policy. We've had a lot of interest from business, and I think it's a very powerful way to engage the public and build understanding for a problem that admittedly has been very difficult to communicate to the public at large. Climate change has always been a relatively abstract problem. We talk about it a lot, but it has been difficult, particularly in the United States, to communicate the elements of the problem in things that are less abstract than things like global mean temperature, which nobody lives in, right? We live in temperatures at a place, not in the global mean. Biophysical feedbacks, that radiative or reflectivity problem, is a new frontier, and I think it raises some very challenging science and policy complications to an already difficult conversation. And one of the things we've been thinking about in the next month, as this group that we're working with is doing some simulations, is to write some very simple, very short pieces on what this problem means and what it could mean for the policy process. Because again, there could be some very nefarious kind of political strategizing going on about countries thinking about the trade-offs between what happens within country versus without. It looks a lot like transboundary pollution instead of what we've thought about it before as a global policy problem. It now has an element that's a lot like transboundary pollution, which is very spatially variant and makes it much, much harder to negotiate between countries. And I think that is it. Thank you very much.
Hi, thank you. My name is Melanie Lonard. I work in this area as well. And so I just thought it might be kind of important for a room of journalists to consider, you know, some of the limitations of the models. And for instance, with the BALA model, it seems kind of important potentially that the temperature changes you're talking about are more integrated throughout the atmosphere rather than on the surface. So there's no consideration of shade. You know, so that of shade, the effect of shade in the model. So
yeah, sure. I mean, you're absolutely right. And again, this is just work that's beginning, and there's lots and lots of complications. There's lots of things that are missing, and we have a long way to go. That's why I don't, you know, I say it's an emerging frontier. There's lots of things that could counteract, in addition to just a lot of non-realism in not only the simulation itself, but it's just in the way the simulations are done. Right. You know, you take 20 climate models, you look at the IPCC AR4 results, and you know, there's a lot of differences, and those are just legitimate algorithmic differences between the way the models run. So this is just one sort of shot across the bow, in which a lot of follow-up work has to occur. There's no question about it. But I think, what it does do, at least I think for me and for people now working on it, is that it raises a challenge. It raises a new and interesting and complicated challenge that, to be completely honest with you, when Roger Pielke and some other people sort of raised some of these concerns even 20 years ago, or in fact, you can go back to the 1980s, and Shukla and others were doing work in the tropics, I kind of, you know, to be honest, sort of poo-pooed it. I thought, no, because when you integrate, it's all going to kind of go away. It doesn't look like it is sort of what a lot of people thought. It doesn't go away on integration. It may be a coherent effect, and clearly we have to explore it.
And just to follow up, I was wondering, the red model that you're talking about, that must be the Betson-Cox-Hadley model?
Hadley model, yeah.
Okay, well, I mean, because another thing with that I found interesting and unrealistic, like I say, is it actually considers that the CO2 fertilization effect that is tending to make plants more efficiently use water would lead to drought, was kind of the conditions in their model for that. So I mean, that seems pretty untested to me and kind of contrary to what the experiments show.
Yeah, I mean, the Cox model is definitely on the outer part of the envelope. That's why I show those two. There are two, in fact, if you look at the C4 MIP that was done recently, it's still the Cox is sort of at one end, and then the sort of blue model, the LPCC, is still at the other end. So it gives you sort of a bracketed bound. All worlds are possible in between. I'm not yet willing to sort of say the Hadley model is completely, you know, unrealistic. I mean, you can quibble with all of them. They all have weaknesses, some things that don't jive with observational evidence. But I still think that they sort of bound the world of possibilities.
Thank you.
Yeah.
I'll leave it where it is. One very short question, then a different one. The first one is, I seem to remember that there's a reflight of the CO2 satellite, at least a European version of that coming up. And the second question is you didn't mention anything about methane, because I understand it's not your specialty, but there are also talk of tipping points with it and sudden release is possible. Do you have any instinct as to whether the scale of these CO2 surprises or those of methane are more worrisome?
Yeah, good questions. There actually is a movement to try to get the same instrument that failed on OCO up on another payload. But whether or not that'll be successful, I don't know. It's, you have to wait in line, for years and years and years to get on one of these launches. But there is an effort to try to get an OCO type instrument up in space. But there are other satellites, there's no question. I mean, we weren't the only game in town. But OCO was a good instrument. I mean, that's not just American bias. It was a darn good instrument. And I think, for example, compared to GOSAT, which is the competitor, I think it was a little bit better for a variety of technical reasons. But we're not out of that game by a long shot. There's no question that we'll be following up. These things happen. Sometimes these rockets don't make it into orbit. On methane, yeah, I mean, I think the methane permafrost feedback is definitely, I probably should be careful about saying this quantitatively, but I would say it's on the same order of magnitude potentially as the CO2 feedback. There's obviously a lot of methane and a lot of carbon that could go into methane emissions because of the type of environment at high latitudes as they melt and become soppy and very anaerobic. And that feedback looks equally problematic without being overly quantitative about it. It's another one of a series of tipping points. There don't seem to be many good tipping points. They always seem to be in the wrong direction. And methane's one of them, including not just methane in soils, but obviously there's deep coastal margin ocean methane hydrates that people have speculated could also be released into the atmosphere. But it's a very, very uncertain business, though it's a fairly large amount of methane could be released, but very uncertain business.
Hi. Going back to those blue and red models you had, what economic parameters, if any, did you use in those to project future carbon emissions? Are you using current numbers? How much of that, included what we're putting out as opposed to what's going out into the biosphere from natural cycles?
Yeah, I think in those two, they're just using one of the IPCC sort of baseline scenarios. I think it's with the AS1 or one of the basic scenarios. So they both use the same. But yeah, it was relatively high growth world, relatively high fossil fuel utilization. But the point is, well, the absolute magnitudes matters, but the relative difference between the two is key. But they did run the same, in that case, they ran the same emissions scenario with the same economic assumptions. It's built into both.
Okay.
Hi, if you could change one thing about the way that journalists are covering climate change, what would it be?
Yeah. Well, I mean, it's funny we were talking at lunch about this, and I still think it's always been a very, very hard communication battle on this problem. Partly because the timeline, the time constants of the problem are, completely ahuman, right? Things happen at decadal to century timescales, and we don't live in that world. Global mean temperatures is a world we don't live in. We live in real places. And so, I mean, I think that as time goes on, I'll say two things. One, I think clearly the problem has to be communicated more in connection with people's daily lives. I mean, that's almost an obvious point, but it's an important one, that the only way, I think, to get people connected to the problem is to bring it right down to their lives every day, which is sort of part of what we were trying to do with Vulcan and Hestia, is sort of get it down into the scale that people walk around and they make decisions and they walk over to a thermostat and turn it on or off and try to get in that world. The other point is, I think, and this has been written about, there has been a lot of it came up before, and this is quite common, that stories are often reported as, this grand debate between these two camps, and they're duking it out. And, within science, that's just not what I've witnessed for, the 25 years I've been doing this. It's just not like that at all. And then the percentages are irrelevant. I mean, I could say it's 90-10, 80-20. It's not that, that's not the point I'm trying to make, is that that's just not the way we're a relatively collaborative community. We don't really have, we debate things, but in a very different cultural context. It's very unique, I think, to science, maybe some other communities too. And that's not quite been captured. It has been because of the interest in driving, a debate and a story that has debates and people duking it out. That, I think, is just not the way it is. That's not the way the dialogue has occurred. We've moved incrementally from having, I'd say we've certainly lowered the uncertainty on some things, but as the previous question noted, we have lots of uncertainty on other things, and we will never not have uncertainty. If we didn't have uncertainty, we wouldn't have anything to do, right? I'd go home. So, I don't know, those are maybe two things off the top of my head that may be obvious, but I think are worth noting. Yeah.
Kind of related to the same question. In the past year, there actually was a survey where, and I'm sorry, I don't remember the source, but it was a major scientific organization, and they compared the views of basically, is global warming a problem? And the scientists that were polled from, many disciplines, like 85% yes. But the public, it was like 45%.
Right.
And on that issue, it was the biggest disparity between the public and scientists of all issues they asked. So what I'm wondering, we need to tell them that scientists are certain that this is something to be concerned about, basically. So is there a scientific resource, summary, something that we could cite that says, look, here's the bottom line for what climatologists and people like you are saying. We get a sense, of the gist, like you say, the gist is that most scientists agree that it's a problem, but how do we as journalists convey that to the public, especially given the huge disparity in the opinion of whether or not there is even a problem?
This is a great question, and it's a hard one. And in fact, I'd almost ask you all, because in terms of resources, I think that most of us think the Intergovernmental Panel on Climate Change and the reports that they produce, including the National Academy, are great resources. They're wonderful. But even those have become politicized. Not internally. Have become politicized by external communities. They've been picked apart as if they were political documents, which they are not. So it's funny. Again, at lunch we were talking about this, and what you come to realize is that, with a certain percentage of the public, and I don't know what percentage that is, but it's not small, evidentiary reasoning is not going to work. It's like evolution. They just don't believe it. And there's a lot of reasons, and I'm not saying those are illegitimate reasons, but it's something that me going on about, this model and lowering uncertainty and how certain something is just not going to crack that nut. Sorry. Never think on your feet.
Well, I think, we see that in other issues, and like vaccines, autism is another one.
Sorry, what did you say? Oh, vaccines, yeah,
Vaccines
right,
with autism,
right.
There's
yeah.
a persistent population
Sure.
that is kind of ignoring scientific evidence. It just seems like the percentage of people is especially high with global warming. And, even I was just speaking with a friend of mine who's a, intelligent, well-educated person. He said, why should we bother spending all this money on, or even talking about cap and trade when it's not even clear that human emissions are contributing anything, and in fact, it's not even clear that we are having global warming problems. And he's a well-educated, well-read person.
Yeah.
So I think it seems that global warming has is a particularly tough one to get through, and it's a larger proportion of people than we see with other issues?
I mean, I agree with that, and I think maybe one way to move the dialogue at this point is to talk about it within the matrix of energy and security. In other words, partner it with other issues that have less of the visceral immediate reaction associated with it, or at least it leverages. So, for example, when you look at those polls, people will overwhelmingly say, yes, we should be more energy independent. Yes, we should conserve more. Yes, et cetera. Right? Sort of in a little bit, dissonantly with the sort of their opinions on climate change. And it could be that by partnering with those other issues and sort of getting away from this sort of hot button, is global warming real or not, you get them into the discussion or get them into becoming comfortable with it through those other avenues that it relates to, like energy independence, conservation, apple pie baseball type things that don't set off the alarm bells. Maybe.
So given the results that you presented from the BALA study, the latitudinal difference and the effect of trees on global temperature, and given some other work along those lines, it sounds like at high latitudes, say Canada and Russia, the evidence right now suggests that planting trees would actually warm the climate further. So what are the implications for public messaging? For instance, if you were being asked by an environmental group in Canada, we're launching a campaign to plant 100 million trees to save the climate, what do you tell them? Do you say, we don't know? Do you say the evidence suggests that it's not a good idea?
Yeah.
Should you wait 5 years for more studies? I'm just curious.
Yeah, I think at high latitudes, it's not like there's room to plant, tons and tons of trees. It's actually in the mid-latitudes where, if anything, we could certainly deforest the tropics a lot more. There's no question about that. But in the high latitudes, there's a lot of, there's a big timber industry, but most of that is regenerative timber industry. We're not necessarily deforesting in big swaths. And there's not necessarily a lot of room to sort of add trees, or at least to the scale that's going to affect, cause a significant albedo effect at high latitudes. It's the mid-latitudes is really tricky, and is exactly where the group that I'm working with right now, we're running a bunch of models, we're doing it all at the mid-latitudes. But I think that, it's funny, we've just put a paper together that we've just submitted that'll take months, if not years, to come out, that is an attempt to try to say, okay, given this emerging, though admittedly uncertain science, does it have a message for managers on the ground? And by and large, we sort of have two stories. At mid-latitudes, afforestation is generally a good thing. You can partner it with energy reduction, like planting near buildings to lower the thermal heat load on buildings, et cetera, et cetera. And that in the tropics, really slowing down deforestation gives you two bangs for your buck. And sort of not avoiding, but staying away from the high latitude story, because it's just, there isn't a lot of room to do much. The result's interesting from this is interesting to learn more about the Earth system and what it does. But I don't think the high latitude story is going to have a big policy impact. But the mid-latitudes definitely will.
If Dr. Gurney's willing to stay behind for a few more minutes, I'm happy to let that happen. But I think for the formal part of this, I want to thank him. Thank you all today. And just let me clarify again, the reception is at 6.